right, let's talk about one of the coolest, most exciting frontiers in AI right now, graph neural networks, or GNNs for short. Now, this is the kind of AI that's built from the ground up to understand one thing, the power of connections. So, you've probably heard about how AI has just absolutely mastered images and text, right? We have things like convolutional networks for pictures, which when you think about it are just neat grids of pixels. And we have transformers for language, which is just a sequence of words. But what about all the data that isn't so neat and tidy? What about the data that's all about how things relate to each other? Because let's be real, most of the world's data isn't in nice, clean rows or simple sequences. It's messy. It's all tangled up in these interconnected networks. And that's the big question. How do you get a machine to learn from that? From the web of relationships that connects everything? Well, the answer, believe it or not, is actually beautifully simple. And that answer is the graph. Now, I'm not talking about the bar charts or line graphs you made in science class. No, in this world, a graph is the universal language for talking about relationships. Okay, so what is it? It's ridiculously simple. You have nodes, you can just think of these as the dots or the individual things, and then you have edges. Those are the lines that connect the dots. The edges represent the relationship between the nodes. That's literally it, nodes and edges. The whole concept boils down to that. Let's make this real. A social network? That's a perfect example of a graph. You, your friends, your family, you're all nodes, and the friendship, the connection between you, that's the edge. See? Super simple. But this idea goes way, way beyond just social media. Take a molecule, for instance. A molecule is a graph. The individual atoms are the nodes, and the chemical bonds holding them together, yep, you guessed it, those are the edges. Or how about a road network? You know, like on a map. Each city or intersection is a node, and the roads connecting them are the edges. Once you start looking for it, you realize this structure is absolutely everywhere. And the list just goes on and on. Scientific papers citing each other, that's a graph. All of Wikipedia with articles linking to other articles, that's a massive graph. The way proteins interact inside our cells, you can map that as a graph too. Even the variables in a computer program. Okay, but here's a key detail we need to get. Not all relationships are created equal. Some are two-way streets, right? We call these undirected. Like a friendship on Facebook. If you're friends with someone, they're friends with you. But some connections are one-way streets. These are directed. Think about one scientific paper citing another. The first paper points to the second, but it doesn't mean the second one points back. This little distinction is actually a huge deal for understanding the data. All right, so we get it. Graphs are everywhere. They're this universal way to describe connections. But how does an AI, a neural network, actually learn from this? How does it think like a network? Well, the first step is to translate this picture of dots and lines into a language a computer understands, numbers. And we do that with something called an adjacency matrix. It sounds fancy, but it's just a simple grid. If two nodes are connected, you put a 1 in the grid. If they're not, you put a 0. That's it. This simple table is basically the graph, just in number form. And now we get to the absolute core idea, the secret sauce of how GNNs work. It's so elegant. A node gets smarter by gathering information from its immediate neighbors. It's that simple. Think of it like this. You learn and form opinions based on the friends you hang out with. That's exactly what a node does. This whole process is called message passing, and it happens over and over in layers. In the first step, a node basically just collects all the info from its direct neighbors. Then it transforms that info, mashes it together with its own current info, and poof, it has an updated state. And here's the magic. When you stack these layers, a node isn't just learning from its friends anymore, it's learning from its friends' friends, and then its friends' friends' friends. It starts to get a sense of its entire neighborhood and its place in the wider network. Okay, so that's the how. We know how they think. Now for the fun part, what can GNNs actually do with all this knowledge? What kinds of amazing predictions can they make? Well, for starters, you can make a prediction about the entire graph as a whole. After the GNN has done its thing and all the nodes have talked to each other, you can ask a big picture question. A great example is with molecules. You can ask, based on the entire structure of this thing, is this molecule toxic? You're judging the whole system. Next, you can zoom right in and make a prediction about a single specific node. For instance, in a social network, you could point to one user account and ask, is this account fraudulent? And what's cool is the GNN's answer isn't just based on that one account's activity. It's looking at its neighbors. Is it connected to a bunch of other known fraudulent accounts? The neighborhood matters. And finally, you can predict connections that aren't even there yet. This is edge-level prediction, or link prediction. The GNN looks at two nodes that aren't connected and asks, hey, should they be? It's looking at their features, their neighborhoods, and predicting the probability of a link. This is exactly how recommendation systems work when they suggest you should be friends with someone. Now, this all sounds pretty amazing, right? But of course, taking this from theory to the real world, especially with giant, messy data, brings a whole new set of challenges to the table. For one, there's just the mind-boggling scale of it all. A big social network can have billions, with a B, of nodes. That's a huge computational problem. And second, there's a unique data problem. With images, you might have millions of separate cat photos to train your model. But with graphs, sometimes you just have one single massive graph to work with. You can't just set some aside for testing in the same way. And this situation leads to two different ways of thinking about learning. The one we're most used to is inductive learning. That's where you learn a general rule from lots of examples, like looking at thousands of molecules to learn what toxic looks like, so you can apply that rule to a brand new molecule you've never seen. But for that one giant graph problem, we often use transductive learning. This is different. The goal here is to use the handful of nodes you already have labels for to fill in the blanks for all the unlabeled nodes in that same graph. It's less about learning a general rule for the future and more about completing the puzzle you're looking at right now. So yeah, there are some big challenges. But despite them, the power of GNNs to understand relationships is completely changing the game for AI. So let's just wrap this up. Why does all this matter so much? At the end of the day, the big takeaway is this. GNNs let AI see the world the way it really is, not as a bunch of isolated data points, but as a deeply interconnected system. They learn from relationships. And this single shift in perspective is what's driving huge breakthroughs in everything from designing new drugs to spotting financial fraud to building better recommendation engines. And that really leaves us with a pretty profound question to think about. If almost everything, from our biology to our society to human knowledge itself, can be seen as a network of relationships, what problems are we going to solve next with this new way of seeing? What's the next big breakthrough? The possibilities really are just about endless.